This is Unit 1 Specimen Paper 2 and Question 11. An endoscope is a device that doctors look in the organs or in your stomach here inside the body, and we can see it here coming in, and they are having a look down the stomach. Identify in diagram A, B, C or D shows the path of light, and what we're looking for is light entering and reflecting off the side of the endoscope. Light won't magically bend. The light travels in straight lines, so it's not that one. These two, this one it's not actually reflecting off the side. It seems to be absorbed and then re-emitted further on, so it's not going to be that one. This one, the angles seem to change each time. It doesn't seem to reflect with the same. The angle of reflection isn't the same as the angle of incidence, so it's not that one. This one looks good, where light comes in, reflects off the side at the same angle, and travels right to the end of the tube. So D is what we want, so we're going to put our cross there. The refractive index of the optical fibre is 1.48, and we've got the speed of light in air. Calculate the speed of light in the optical fibre. So we've got 3 marks here, and you really should get these 3 marks. There shouldn't be any excuses. You know the equation, n equals c over v, where n is our refractive index, c is the speed of light in a vacuum, and v is the speed of light in the medium. So you can do this one of 2 ways. You can put the numbers in and evaluate straight away, or I'm going to rearrange the equation, because we know what the refractive index is, 1.48, and we know the speed of light in our, in air we're going to have here. Speed of light in air, 3 times 10 to the 8 meters per second. And the speed of light in the fibre, that's what we're trying to work out. So I'm going to rearrange this. I'm going to, as I need V on its own, so I need to bring V up, so NV equals C, and then I want V on its own, so I need to get rid of this N by dividing both sides by N, so V equals C over N. And now I can just put these numbers in. That's our 3 times 10 to the 8, and N is 1.48. So we just get our calculator, 3 times 10 to the 8 divided by 1.48, and that is that big number there, but that would be 1, 2, 3, 4, 5, 6, 7, 8. So it's going to be 2.03. So 2.03 times by 10 to the 8, and I'm going to put my units there. So 2.03 times by 10 to the 8. Why have I said 2.03? Why have I gone to 2 decimal places like that? Well, we've got a refractive index there. That's sort of 3 significant figures. So I'm going to use the same here. A technician who's using the endoscope accidentally bends the optical fibres to a very sharp angle, but they don't crack or break, but it's just this very sharp angle that they're concerned about. So that is, if our endoscope might be okay if it's kind of like that, but if we go like that, it might be too much. So the light in the cable is going to hit. It's going to sort of, there, and then it's not going to be reflected in the medium, because this medium that the cable is dense. It's going to be kind of glass-like cable, and so the light is going to be less than our critical angle, which is the key thing there. So if you think of, you've got your normal there, and the critical angle is the distance away from the normal. So if that's 2, if that angle there that it hits is less than our kind of critical angle, then it won't get reflected. So we just need to put that into words. And remember, the key thing to remember with these cables is that it relies on the light reflecting, and so it's got to be higher than the critical angle, and that's how these things work. So when we bend it, so explain why. So any answer that starts off why, we're going to say because the light in the cable hits the side of the cable at an angle less than the critical angle. So the light is not reflected. That's the answer that they wanted. We could possibly come up with another solution to this. Say if the bending wasn't quite so bad, but we had lots of kind of bends in there, then we're going to have more reflections, and so light is going to have to travel further, and if you've got more reflections, then that's going to reduce the intensity or the brightness of the light. So we could also say bending causes more reflections, so light has a longer path. So more will get, every time you have a reflection, you're going to get some absorption of light. So more reflections, more light's going to get absorbed by the cable. So more absorption by the fibre. But we don't really need that, because our main answer is above there. And then we've got last little bit, optical fibres use digital signals for communication, and they are clear and high quality, and a lot of data. So it's telling us quite a bit there. So these digitals are clear, high quality, a lot of data. And we need one other advantage, so we can't talk about those. And again it says explain. So we're going to start off because. So long distance communication, and one of the main things is because the signal can be regenerated. So that means that when we lose a bit of the signal, so we lose a little bit of the signal due to sort of some interference, then because it's essentially zeros and ones, then we're still picking up these zeros and ones, and then we can kind of boost the signal, so stronger but still the same zeros and ones. So the signal, the information hasn't actually changed, we're able to kind of amplify it and keep the quality. So a greater distance is possible, and then no attenuation changes. Really, there's your 2 marks there. Can be regenerated. Whereas if it was analog, the noise would also be amplified. If you made the signal stronger again, every time you pick up some noise, it becomes part of the signal. And that's 8 marks.